In this series of videos, we're going to talk all about a geometric application of the material about integrals we've learned so far. And that application is computing the area between two curves. So in this video, what I want to do is just explain the problem and what it means to compute the area between two curves. So let's start with a question. What is the area between the curves y equals f of x and y equals g of x from x equals a to x equals b? Well, let's take x equals a to x equals b, and let's graph y equals f of x, this top curve, and y equals g of x, this bottom curve. So the area between these curves from x equals a to x equals b is we'll just draw vertical lines at x equals a and x equals b. And the area between the curves is what you would think it is. It's the stuff that lies below one curve and above the other. Okay, so what does this have to do with integrals? Is there's another way to think of this, which is it's the area under the graph of f of x, again from x equals a to x equals b. That's everything under the top curve. But now we want to subtract out the part that's also below the bottom curve. So minus the area under the graph of g of x from x equals a to x equals b. Okay, and we have ways of expressing these two areas using integrals. This is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. And using one of the properties of integrals that we know, the integral of the difference of two functions is the difference of the integrals of those two functions. So this whole thing is the integral from a to b of f of x minus g of x dx. So informally, what's happening is we're taking the integral from a to b of the top function minus the bottom function. Because here y equals f of x, that curve is above y equals g of x. So we're taking the area below the top curve minus the area below the bottom curve. Okay, so this is the most basic picture. Let's try to understand what happens in a situation that's a little more complicated. Let's discuss what happens if one of those curves goes below the x-axis. Because remember, this integral from a to b of f of x dx, that's the signed area under the graph of f of x. So that's the area under f of x that's above the x-axis minus the area that's below the x-axis. So what if one of these curves goes below the x-axis? Well, in that case, what is the integral from a to b of f of x dx? Well, it's just all of the area below this top curve, including some of this that's actually below the curve y equals g of x. And then what is the integral of g of x from a to b? Well, it's this part that's above minus this part that's below. So what is the area between these two curves? Well, it's still the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Why is that? Well, in the part where they're both positive, it's the same reasoning as in the first example. You have all the area below the graph of f of x, but some of this below the graph of g of x you don't want to count. So you have the integral of f of x counts all this area, and then you're subtracting off the part that you don't want to count that's right here. Okay, so what about the part where g is negative? Well, you have this part above the x-axis that is the integral of f of x on this interval, and then the integral of g of x on this integral is negative, right? Because it's the signed area. The part here is below the x-axis. So when you put in this minus sign, what we're doing is we're actually adding in this positive area. So what is the area between these two curves? It's the part under f of x and above g of x. It doesn't matter whether f and g go above the x-axis, below the x-axis. The formula is the same. So it's the same even if the curves go below the x-axis. Okay, so I just want to talk about one more thing in this video, which is when we talked about area, what is area? How did we define area? We defined area as this limit involving sums of areas of more and more and more rectangles. And now we're just talking about the area between two curves. So I just want to show you that you can still understand area in terms of limits involving sums of more and more rectangle areas. For example, let's look at this picture. We want to understand the integral, the area between the curves y equals f of x and y equals g of x between x equals a and x equals b. So if we approximate this area by a bunch of rectangles, we have to pick a bunch of sample points, right? These are our points xi, and we can look at f of xi and g of xi. Let's say that we want to use left endpoints for our rectangle heights in approximation. So now we're going to make a rectangle between each of these bases that goes from f of the left endpoint all the way down to g of the left endpoint. Okay, so this is not exactly going to be the area that we're looking for. It's just an approximation. But the point is that so each rectangle has base delta x, just like before. This b minus a over n. And now the rectangle heights, well, what is the length of this line? It's f of x0 minus g of x0. Right? So if g of x0 is below the x-axis, f of x0 is this part. Let me highlight with a different color. F of x0 is this part, and minus g of x0 is this part. So what you get by this approximation, where your rectangle heights are f of xi minus g of xi, is you get a bunch of rectangles that go between your two curves. And for the same reason that when you take the limit of Riemann sums, you get the area under the graph of a function, or the signed area under the graph of a function, here, as you take more and more and more rectangles, you get a better and better and better approximation for the stuff under your top curve and above your bottom curve. So you're never going to have to compute the area between two curves using this rectangle area approximation. But I just want to show you how this geometric topic fits into the same kind of framework that we first used to define area.